Welcome. This review is going to cover Lab 7, Compounds and Their Bonds. While the pre-lab quiz and the lab report themselves have a similar set of ideas, we're going to go through those ideas, look through the lab report, and do a few examples to try to help make sense of this chapter, make sense of this lab. It's not so much a lab as it is. Not so much a lab as it is kind of almost like additional lecture practice. You'll see what I mean as we go. Okay, first things first. The objectives for this lab are, zoom in a little bit here, write the electron dot Lewis symbols for atoms and ions, write the correct formulas and names for ionic compounds, including those with polyatomic ions, write the correct formulas and names for molecular compounds, and use electron dot structures or Lewis structures of a compound to predict its shape and polarity. Now, the second and third one are reviews of something you should have learned very early in the year, how to write and name ionic compounds and how to write and name simple binary molecular compounds. The Lewis dot symbols for atoms and ions are also relatively simple and something that you may have come across earlier on. We're going to review those real quick though. So first of all, if we look at a periodic table and you look at sodium, sodium is one of those elements that a periodic table is in the first column. So if I were to draw a periodic table, kind of just a rough sketch here. So I have the first column in the periodic table. The second column is slightly smaller just because it doesn't include hydrogen. And then we got a couple rows down, and we got this D block over here. And then we go back up, and then we have this P block area. And then last but not least, we have the last one, which is our noble gases. Okay, so one of the things that you probably picked up when doing electron configuration, which is something that should have been covered by this point in time, is that the outermost electrons of any particular atom are its valence electrons. So this is the electron configuration for sodium. And the outermost electrons are going to be those of the highest energy level. In this case, the highest energy level is the 3. So that's these, 3s1. Now, so for sodium then, it always wants to be like the closest noble gas. And the noble gases have a complete outer shell. Now, it would take quite a bit. It would take quite a bit for sodium to gain enough electrons to complete the third shell. So instead, it tends to lose electrons to be like the closest noble gas. And in fact, all metals are like this. All metals will have a tendency to lose electrons rather than gain. So lose electrons to be like the closest noble gas. In this case, sodium will lose its 3s1. You see the image of the electron leaving, and that leaves, and if I may, I'll go ahead and draw. So you have 11 protons, and you have 3 shells. That's crazy. Go ahead and delete that. Let's try it again. There are 3 shells around this sodium. In the first shell, and I'm going to draw these in a different color to make it a little easier to see. In the first shell, there's only 2 electrons. That's that 1s2 we were talking about. In the second shell, you have the 2s and the 2p. Now, the 2p orbitals are actually shaped like this, and the reason that there's 6 of them is because there's actually vertical, horizontal, and then like basically x, y, and z axis. So up, down, side, side, in, out. There are 3 of them, and each one of those has 2 electrons. For the purposes of what we're drawing here, I'm just going to draw them in this order as a second shell. So the second shell has 8. It has 2s2 and 2p6. That's a total of 8 valence electrons. So 1, 2, 3, 4, 5, 6, 7, and 8 valence electrons. And then that 3s1, so there's 1 electron in that third shell. That's this electron here. So it's going to lose that outer electron. It'd be like the closest noble gas, which is neon. Neon has an atomic number of 10 protons, 10 electrons. And so it's going to have that same 10 positive charge. It's going to have a 10 positive charge, which is a little bit less than sodium. But it'll have the same two shells. It'll have the shell number 1 and shell number 2, which I'll draw here. So you got your shell number 1, shell number 2. No, I haven't drawn that perfectly. It's a little hard to draw on this board. But effectively, by losing an electron, sodium becomes like neon. So if you're going to draw the Lewis structure for a neutral sodium atom, this is a Lewis structure for an atom, not a compound, you would just draw the outermost electrons on that symbol. In this case, there's only one. I draw it like this. If you had the next atom, which is magnesium, magnesium has one more electron, so it would have that outermost one. Instead of being 3s1, it would be 3s2. And so for 3s2, magnesium, I might draw it like this. Although by convention, when we draw these Lewis structures, we tend to try to put one electron on each side before we double up. So instead of drawing magnesium like this, we would end up drawing it, in most cases, like this. Let's continue. So an oxygen atom, likewise, its outermost if we look at its outermost electron for an oxygen atom, and actually this is not quite correct for an oxygen atom. I'm actually going to skip this. As an oxygen atom, the electron configuration should be 1s2, 2s2, 2p4. That's once again due to its position on the periodic table. Well, it's also in the 6th column. So if you look at, or rather in the 6a column, on the periodic table, one of the things you may note is that on the columns of the periodic table, there's typically a label that goes above them. The first column, it might say 1a. And the second column, for example, it might say, do this, 2a. The A columns here, the number before the letter A tells you how many valence electrons it has. Of course, you have then the transition metals, and then it goes back up, and it goes over, and of course, you'll start to see, okay, well, this is going to be 3A, and then there's 4A, 5A, 6A, 7A, till you get the noble gases, and they're 8A. Those numbers tell you how many valence electrons you have, so you don't really actually even need to do the electron configuration. Oxygen, it happens to be in the 6th column. So this is going to, the electron configuration is as I've drawn it. So the outermost electrons for oxygen are in the 2nd energy level. That's going to be 2s2, 2p4. That's a total of 6 valence electrons. So when you're doing the oxygen atom's electron dot symbol or Lewis symbol, you draw the symbol for oxygen, and then you put 1 on each side. So 1, 2, 3, 4, and you keep going until you get to a total of 6. After each side has 1 electron, then you can put an additional electron. So 5, 6. Now notice in this case, the way that I've drawn it, I have pairs on the bottom and on the right. And the other one, and the one that it shows over here, it has the pairs on the top and on the left. Does it matter? No, not really. Now if I add 2 electrons, as it's shown here, I add 2 electrons to the oxygen atom, I'm going to basically be adding electrons here and here, giving a -2 charge and making it like the closest noble gas. And the closest noble gas to oxygen is once again neon. So again, this is not the correct electron configuration. This is an error in the book. This is kind of surprising error. Really should have been screened better. But the electron configuration, once it adds 2 electrons, is just going to be 1s2, 2s2, and 2p6 rather, after it gains 2 electrons. There we go. 1s2, 2s2, 2p6. So that 8 electrons there. And so that is going to be a complete octet. Now it's going to be like neon. So that's basically how you do those Lewis dot structures for atoms. Now let's take a look at ionic compounds. This should not be too much of a stranger to you because you should have had experience with this previously. While you can draw these Lewis structures for showing how the electrons are transferred, sodium atom has 1 valence electrons, which will transfer to oxygen, and oxygen wants 2, so you need 2 sodium atoms, each one giving up 1 electron, and then you form the sodium oxide formula with 2 sodiums and 1 oxygen. However, it's really not necessary to show all this. Really not necessary to show all this when we're actually working it. So in this case, it kind of this is just kind of a review of what it showed with the valence electrons, and this is going to be useful for determining what the charges are of the different atoms that we're putting together to form these ionic compounds. So group 1A loses 1 electron, it'll be a +1 charge. 2A loses 2 electrons, it'll be 2+ charge. Once you get to group 4A, it would either have to gain 4 electrons to be like the noble gas, or lose 4 electrons to be like the noble gas. And it doesn't really like to do either, honestly. The truth is, what's shown here is not totally correct. You do actually get sometimes, in rare cases, -4 ions or +4 ions. But they're so rare and they don't occur very often that we generally say this usually doesn't happen. So we say none here. It's a little bit of an oversimplification. Okay, so if we look for atoms that tend to have 5 valence electrons or more, you're looking primarily at the nonmetals here. When we're talking about the nonmetals, they have a tendency to gain electrons, usually. And nonmetals are going to have a tendency to gain electrons. So oxygen, fluorine, phosphorus, nitrogen, chlorine, bromine, sulfur, they're all going to tend to gain electrons to be like the closest noble gas. If you have 5 valence electrons, you get like the closest noble gas. To get to 8, it has to gain 3. 5 + 3 is 8. And therefore, it'll be -2. If you gain negative thoughts, you develop a negative attitude. So if electrons are negative, you gain negatives, you're going to become -3. If you lose negatives, you become a positive person. So losing electrons makes you a positive ion. 7, only need 1, gain 1, -1 charge. 6A, 6 valence electrons, you only need 2 to get to 8, you gain 2 electrons, a -2 charge. The pattern is pretty straightforward. So let's look at some of these naming and writing of ionic formulas. In the cases of metals with variable charges, like those are the transition metals, you can't predict what their charge is based on the periodic table, based on what group they're in. So you have to look at what they're bonded to, or it has to be given to you. So you'll either be given a formula, in which case you can determine what the name is, or you'll be given the name, in which case you'll determine what the formula is. but you have to be given either the formula or you have to be given the charge in the name of those transition metals. So those transition metals are going to have a Roman numeral next to them. That's what this is. It tells you the charge of the metal ion. And Roman numerals are only used with positive ions, not negative ions. You don't have transition negative ions. Transition metals will always be positives. So, iron 2 has a positive 2 charge. Iron 3 has a positive 3 charge. And so on and so forth. So, I'll go ahead and work with you on examples of how this works when we get to the actual report. But you need one or the other. You have to be given the charge in some way for transition metals in order to name it or write the formula. Now there are transition metals that are in the transition metal area that have a tendency to be, they tend to only have one particular charge. They don't have multiple charges. And for these ones, you don't actually get a Roman numeral, so you kind of got to just memorize them. Turns out it's at the corner of the periodic table. There's this area I like to refer to as the magic staircase. It's like this little staircase of elements that, even though it's on the transition metal side of things, they have always the same charge. And I'm going to actually draw this in bigger form. So there are 3 elements that are going to be +3s, 2 elements that have a tendency to only be they're going to be +2s, and 1 element that's a +1. And effectively, those elements are as follows. So let's go ahead and finish drawing the boxes. So the 3+ element is actually first one is actually one you can predict from where it is in the table. This is a 3+ aluminum charge. And then underneath that is gallium. And gallium has a tendency to be only a 3+ as well. And then indium has a tendency to be 3+ as well. Although the truth is, all of the metals that are not in the first 2 columns, here and here, they have multiple charges except for this little staircase, which I'm drawing now. You should assume that all metals that are not part of those first 2 columns or in the staircase can have multiple charges. So zinc is always going to be a +2. Cadmium is always going to be a +2 or 2+. And silver is always going to be a +1. You have 1 + 1, 2 + 2s, and 3 + 3s. This neat little staircase to kind of help you remember those elements that will always have the same charge. Okay, let's go on from there. You also have, of course, your polyatomic ions, which you should actually have memorized at this point. If you have not memorized them, this might be a little bit more difficult for you. But I'm not going to spend a whole lot of time on that because that is something that you're kind of already supposed to know. Molecular compounds, drawing the Lewis structures of them, I'm actually going to go over in more detail how to do that in a bit. Let's go ahead and skip ahead to the actual lab itself. And in the lab, this is actually on page 13 of the lab form. This is the first thing that you actually need to complete on the lab, and you actually have to download this or copy this table, this ion formation table that you're seeing right here. You have to copy this and input it into the. I'm actually going to go ahead and share my screen right now. Let's see. Lab report. There we go. So this is the lab report. It says data and report submission, compounds and their bonds. Complete the ion formation table and upload an image of your completed table. So this ion formation table that it wants you to complete is none other than that I just showed you. Let's go back to that table that I just showed you. I'm going to go to the appropriate page, which is 13, that page. And what you need to do effectively is write out the electron configuration of each of the different atoms, and write the Lewis dot symbol of the atoms, whether it loses or gains electrons, the electron configuration of the ion, and the ion charge. It has one example done for you. I'll do a couple more, but the rest you'll have to kind of complete on your own. So if you're looking at the, we'll skip ahead. I'll do chlorine and calcium. So if you look at chlorine, the electron configuration of chlorine, if you look at its atomic number, see it's 17. It's also in the third period. And basically, it's just going to be 1s2, 2s2, 2p6, and that completes the second row, but chlorine's in the third row. I go to the next one down, it's 3s2, and then it's chlorine's in the 3p block, the p block in the third row, so it'll be 3p, and then I count over 5 boxes to get E, because each box in the periodic table actually represents a place for an electron to be. That is the electron configuration for chlorine, a chlorine atom. The Lewis dot symbol, and actually, you know what? I'm going to actually take a moment here and go over this in a little bit more detail, because I want to show you compounds and their bonds table down here. Okay. I want to go to periodic table for electron configuration. I'm going to zoom in on this just a little bit. I see chlorine is actually right here. Chlorine in the third period. So this periodic table for electron configuration makes things much easier, because when you fill up boxes, each one of these boxes in the periodic table represents a place for one electron. So when you're writing the electron configuration for an element, you fill up the boxes until you get to the atom that you're trying to find its electron configuration for. So always start out at the first, just like a book, start out at the top, start out on the left, so read left to right, and then go to the next line. Then left to right, go to the next line. So this is 1s2 because there's 2 boxes, one for hydrogen, one for helium. 1s2, 2s2, 2p6, we're up to neon. Then we go to the next line. 3s2, we're up to magnesium. And then 3p. In the 3p, I have to get to chlorine, so I fill up 1, 2, 3, 4, 5 boxes until I get to chlorine. Once I 5 boxes when I get to chlorine, so 1, 2, 3, 4, 5. So it'll be 3p5. So that's why that is why for chlorine, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Let's go back and finish out chlorine. Okay, so the electron dot symbol for chlorine is going to have 7 dots. That's going to be 1, 2, 3, 4, 5, 6, 7. Now, if I was a little bit more careful, I would have done 1 on each side before I do 1. But since it's 7, I'm basically going to have completely full except for 1. One side is only going to have 1. Now, in this case, is it closer to being empty? Is it closer to the previous noble gas or the next noble gas? Chlorine's a lot closer to argon than it is to neon. A lot closer to 18 than it is to 10. So chlorine's going to gain 1 electron. And I would write gain 1. And so the electron configuration, if it gains 1 electron, it's just going to have 1 more than it did previously. It'll be 1s2, 2s2, 2p6, 3s2, 3p6. And note, and I should mention, back of the electron dot symbol for chlorine, you see you have 7 electrons around here. Where do those 7 come from? Well, those are the valence electrons. Those are the electrons from the highest energy level of that particular element. The highest energy level we can see from the electron configuration here. The highest energy level is 3. So there's 7 electrons in that energy level, so that's why there's 7 around the chlorine. Alright, so now if it gained 1 electron, its charge is going to be 1 minus. The ion symbol then is going to be Cl, a minus charge. I don't have to put 1 minus because 1 is assumed. If it's a 1, you can assume the 1 is assumed and I just write the minus. If it's 2 or more, then I have to say minus 2 or minus 3 or 2 minus 3, etc. Now, ion name. With metal ions, the name is the same as the element name. Say sodium ion, or sodium. But with a non-metal ion, it actually has its name changed. Non-metal ions get an IDE ending, uses the first syllable. So chlorine, the first syllable is chlor. And then you add the IDE ending, so IDE. So oxygen would be oxide. Nitrogen would be nitride. Chlorine, chloride. Chlorine, chloride, etc. There are a couple exceptions, like for selenium, instead of saying selide, I would say selenide. And likewise, iodine, I don't just say iodide, I say iodide. So there are a couple exceptions, but you change the ending to an IDE ending. Usually it's just the first syllable that you keep, and then you change the ending to an IDE ending. All right, there we go. Going back then to the main report, I'm going to go ahead and share my screen again with that. After you've completed that ion chart and you've saved it into some sort of a file, you can either draw it and scan it, or you can copy and paste that image, or make an electronic document, however you want to do it, but you'll have to upload the file here by clicking on the or dragging and dropping. You can also, after that, you're going to go to the Ionic Compounds section. As referred to an image of the compound below, then look it up and record its density. Look up and record its density and melting from the reference materials. As the compound it wants you to look up is sodium chloride, NaCl. Well, honestly, you probably have seen that, so you probably don't even need to look it up. But there is actually a page specifically where it wants you to look. In Labflow, if you go down to the compounds and their bonds lab, towards the bottom, you have the first line right here of everything from the pre-lab quiz to a video on how to name ionic compounds, etc., and covalent compounds. So there's also in the introduction that has that table 1. There's also sample images, and this is what you're going to need to complete the lab. So if I open up the sample images tab, I see sodium chloride. Well, I can see, okay, well, this is just kind of a white crystalline solid. If I go back here, I say, okay, well, I'll go back to the report. I have the white crystalline solid. So for sodium chloride, Go back to the beginning, sorry. I could just say this is white crystals. The density, for that I'm going to have to look it up. So I can actually look it up and just say density of salt, density of NaCl. If I look up sodium chloride, I can even go to Wikipedia, but there's more substantial places to go other than Wikipedia. But Wikipedia is actually pretty good at a lot of these things. But if I want, I can, under the properties here, under physical properties inside, the density of 2.17 grams per centimeter cubed. So I could, or 2.17 grams per milliliter. I could go ahead and put that into the Labflow report. I could say 2.17 per milliliter. Then I could look up the melting point. And the melting point, it says, is 800.7 degrees Celsius. That's pretty big. 800.7. 800.7. Go back to the Labflow report, 800.7. So you can find these melting points, and this is degrees Celsius. I'll do a little superscript O for degrees, and then I'll take the superscript off Celsius. So degrees Celsius. So yeah, basically that's all you really have to do for this part, is use reference materials, record the density and melting point from reference materials. So there's reference materials in the actual labs of the sample images here. There's an image of water, there's an image of potassium carbonate, there's an image of iron chloride. And as far as the other reference materials it's referring to, it might also have this up on other things, but you can also look it up on the internet. After that, you're going to do the formulas of ionic compounds. And so I'll do one of these with you. The rest of these kind of entrust to you, but this first type of ionic compounds, relatively simple ionic compounds. There are no polyatomic ions here. You just have to figure out what the charge of the different ions are based on the periodic table. Calcium, look at the periodic table. Calcium's in the second column. It has an atomic number of 20. The closest noble gas is 18, argon. So calcium's going to tend to lose 2 electrons, and if that's the case, it'll be a 2+ charge. The calcium will lose 2 electrons, Ca. And because it loses 2, it'll be a 2+ charge. Phosphide, if I look at the periodic table, phosphide is phosphorus. It is 15 electrons. The closest noble gas to phosphorus is actually argon, which has 18. So phosphorus is going to gain 3 electrons. Electrons are negative. It gains 3 electrons. It gains 3 negatives, so it'll be a -3 charge. Phosphorus will have a 3- charge here. So here's the deal. If I want to find the formula for this, I have to balance the charges. There's 2 ways to do this. One is to use the lowest common multiple method. The other is the crisscross method. I'm going to show you both real quick. I have calcium with a 2+ charge. And I have phosphorus with a 3- charge. The lowest common multiple method says do the multiples of the charges, okay? In terms of absolute value here. But multiples of 2 and 3, multiples of 2 would just be counting by 2. So I have 2, 4, 6. Those are multiples of 2. I also go 8, 10, 12, etc. Multiples of 3 would be like 3, 6, 9, 12, 15, etc. Just counting by 3. So the lowest multiple that they both have, the lowest multiple they share and have in common, is 6. So how many calciums would I need to get a total positive charge of 6? Calcium's charge is 2+, so 2 times what is 6? And notice this is also the third multiple. This is also the third multiple of calcium. The third multiple means I need 3 calciums. I put calcium and then a 3. Now phosphorus, the lowest common multiple is likewise 6, but the charge of phosphorus is 3 minus. How many phosphides do I need to get a total negative charge of 6? Negative 3 times what gives me 6? 2, right? And notice it's also the second multiple. It's the second one down. That tells you you need 2 phosphoruses in this compound. So this is going to be Ca3P2. That's one way to get the formula, the lowest common multiple method. Another way is called the crisscross method. The crisscross method involves taking the charges. I have a 3 plus here, and I have a, whoops, that's a mistake, 3 minus. I not have a 3 plus. Why? I have a 2 plus. Calcium's a 2 plus. The crisscross method says, well, okay, I'm going to take my charge here, I'm going to bring it down to make it the subscript here. The charge for phosphorus, bring down the subscript here. I'm not just going to write the charges as positives or negatives, I'm going to actually just take the absolute value. In other words, this 3 minus tells me I need 3 calciums, this 2 plus tells me I need 2 phosphoruses. This is going to give me a Ca3P2. Notice I did not put a negative 3 in front of calcium. I did not put a positive 2 in front of phosphorus. I just put 3 and 2. There's a good reason for that. These numbers, 3 and the 2, they do not tell you the charge. They do not tell you the charge. What are those telling you? These numbers, they tell you, these numbers tell you the number of atoms. Subscripts, those are the 3 and the 2 on the bottom there. Subscripts tell you the number of atoms of each type. That's what subscripts tell you. Subscripts tell you the number of atoms of each type. Superscripts tell you the charge. I'll write that too. Superscripts, those are the little positives and negatives up on the top. Superscripts tell you the charge. That's the charge is, basically the balance of protons and electrons. If you have more protons than electrons, it'll be positive. If you have more electrons than protons, it'll be negative. So keep that in mind. Also, there is a danger of the crisscross method. Crisscross method can lead to confusion on the subscript superstring, like which one tells you what. Crisscross method can also give you the wrong answer if you forget to reduce. So like, for example, if I had something like this where it's Pb and a 4 plus charge, and S, the 2 minus charge, if I just crisscross that, I might say, okay, well that means that this is Pb2 S4. That's actually wrong. That's actually not correct. That's not what the formula should be. I need to reduce this to the lowest whole number ratio. And so since the 2 and the 4 can both be divided by 2, that means I would get Pb S2. The lowest common multiple method automatically reduces it to the lowest whole number ratio. So it's a little safer in that regard as well. You can choose to use whichever one works best for you. Let's go back to the problem. So the calcium phosphide, I now know that this is going to be Ca subscript 3. Subscript 3, come on. And then P subscript 2. That's how you do that. Now, if you have the formula and you're trying to give the name, if it's one of those main group elements, the ones that are not transition metals, the ones that cannot have multiple charges, I don't need to indicate a Roman numeral with the name. In this case, first let's write the name of the ions. So barium, in this case, look where it is on the periodic table. Second column, barium, towards the bottom. That's going to be close to xenon. It's going to lose 2 electrons. It's going to be a positive 2 charge. So barium's going to be a 2 plus charge. A little superscript there, 2 plus. Chlorine, right next to neon, it'll gain 1 electron. It'll be an F minus charge. Once again, I don't have to put the 1 minus. I'm just going to put minus. Now, it might still accept it if you put 1 minus, but whenever you save them, sorry, and just put minus. Now, the name of this is actually really simple. It's really simple to name this. I just put the name of the metal exactly the way the metal is on the periodic table, so it's barium. And then I put the name of the non-metal with an IDE ending, because remember, the negative ions have their endings changed to IDE if they're single elements like this. Polyatomic ions, you don't have to change the ending. With single elements, they're those non-metal ions, and they get IDE endings. So this is going to be fluoride, so FLUORIDE, barium fluoride. The same thing works with the rest of these. Now it has a section on metals with variable charges. Now once again, you're going to do kind of that same thing, iron-free chloride. You're going to look at those sample images, look at the iron-free chloride, give the description, and look up the density and melting point and all that good stuff. So, going back to the report, you know how to do that. And it says, complete the table with the positive ion, negative ion, and the name. Well, this is actually even easier than the previous one, because in this case, it actually gives you the charge. So iron 2, that's just going to be Fe with a 2 plus charge. Fe with a 2 plus charge. Copper 1, just copper with a 1 plus charge. Zinc and silver, those are the tricky ones. Those are the ones you got to look in the periodic table, so that rather you have to remember the magic staircase, so to speak. The zinc, it's in that zinc and cadmium, they always have plus 2 charges. It's going to be one of those special ones. And unfortunately, you're going to have to memorize it if you haven't already. You're kind of supposed to a couple months ago. But yeah, so let's say zinc is the Zn2 plus, and you have oxide, right? Oxide is just oxygen, 2 minus charge. Oxygen is 2 minus charge. In this case, if the charges are the same, you've got a 2 plus and a 2 minus, you don't have to crisscross. If the charges are already the same, they're already balanced, you only need one of each. The formula for this one would just be ZnO. And so just fill out the ions using the periodic table for the nonmetal ions, and for the transition metal ones, just go ahead and slap in that charge it gives you. Copper 1, 1 plus 1. Copper 2, plus 2. Remember, it doesn't tell you how many of them there are. You're not going to put that for example, this number 2 here for copper, that doesn't tell you you're going to put a subscript 2. It tells you that the charge of copper is 2. The number from the formula is not actually going to be 2 in this case. All right. Let's name some of these more challenging compounds. This is where it gets a little more tricky. You figure out the charge of the ion. That's what allows you to name these transition metal compounds. So since copper here had a plus 1 charge, I say copper, parentheses, Roman numeral 1, close parentheses, space sulfide. Let's look at this iron, Fe and oxygen. This is where doing that little thing that I showed you earlier can help. The lowest common multiple method. I'm going to go ahead and do a whiteboard here. At Fe2, Fe2O3. I'm trying to name this. Well, the transition metals, you can't actually figure out what the name or what the charge of the metal is directly, so you have to find indirectly. So what that means is you're going to have to figure out what the total charge of the nonmetal ion is, because in an ionic compound, the total positive charge has to be equal to total negative charge. So oxygen here. Oxygen, if you look in the periodic table, you can tell that it's going to be a 2- charge, right? I have 3 oxygens, so 2-, 2-, 2-. Well, that's going to be a total of -6. Well, if the positive charge is equal to the negative charge, this is going to be a +6 for the total for the irons. Now I have 2 iron ions, but I don't know what their charge is. I know the total positive charge is +6. So 2 ions, that gives me a total of +6 charge. So 2 times what gives me 6? I can actually just take +6, divided by the number of ions, 2. 6 divided by 2, that's a +3. So each one of those iron ions has a charge of +3. Since I already know that oxygen is a -2 charge, I can now very easily figure out my formula either with the lowest common multiple method or with the crisscross method. I do lowest common multiple. Okay, this is 3, 6. Actually, I don't need to do that because I already have the formula. I already have the formula up here, Fe2O3. And all I have to do now is name this. So this is just going to be iron. Because it has a charge of 3, it's going to be iron 3. Roman numeral 3 is just 3 I's. So iron 3 I's, those are not 1s, those are capital I's. Iron 3 oxide. And so this will be Fe plus. This will be an O minus. And this is going to be iron, Roman numeral 3, oxide. And then you can proceed to do the same thing with the rest of these. Now note, if it's one of those special ions, silver is not actually really a transition, well, it's not a transition metal in the sense that it doesn't have a changing charge, right? But silver, it's not going to be silver 1 or silver 2. Silver always has a +1 charge, so it'd just be silver oxide. This one. Watch for those. Now, next one, physical properties. In this case, this is potassium carbonate. Once again, that you're going to go back to this sheet, look down at potassium carbonate, describe its appearance. Next, density melting point you can look up on the internet or with reference materials. Then, looking at the formula. So, this isn't really any more difficult than anything you've done previously. You just have to use the polyatomic ions. And this is just about having the polyatomic ions memorized, honestly. You do have to have them memorized. Unless your professor gives you a sheet, which not all of them do. Alright, let's go to chromium hydroxide. If you just have one of the polyatomic ions, like in the example above, Ca+, CO3, 2-, I need 2 potassiums for every 1 carbonate, which is K2CO3. If you only need 1 polyatomic ion, then you do not use parentheses with the polyatomic ion. However, if it's like this, chromium 3 hydroxide, I have Cr, and it's going to have a 3+ charge because it says chromium 3. I also have hydroxide. That's going to be a 1- charge because hydroxide is always 1-. You just have to know that. And I'm going to need 3 -1s to balance with the +3, so the total positive is equal to the total negative. So this is going to be chromium, parentheses, OH, close parentheses, subscript 3. I need to use the parentheses when I need more than one polyatomic ion. And that's honestly the only tricky part about this. It's the only thing you need to watch for. As far as these polyatomic ions, you can actually find these listed in that introduction document. Here's those polyatomic ions. They're listed right here. Looks like it's listed on page 5. Page 5. So here's some polyatomic ions, the ones that are going to be in the report right here for you. All right. Going down. Naming these ionic compounds, once again, not too hard. First, you have to look and see if the element is a transition metal or if it's a main group element. If it's a main group element like strontium, you don't need a Roman numeral. Just look at the periodic table, figure out its charge. If it is a transition metal, you need to figure out its charge before you can name it. So iron, in this case, hydroxide's a -1 charge. There are 3 of them. That's a total of -3. So iron has to be a +3. This will be Fe superscript 3 plus, and then the negative ion will be OH superscript minus. Now, because iron is a transition metal, I do have to indicate the charge in the name. If it was a main group element like calcium, there's no Roman numeral, there's no charge. In this case, it's iron, Roman numeral 3, that's 3 capitalized. If I put once or else, it'll be wrong. 3 capitalized, iron 3 hydroxide. That's it. Go ahead and proceed with the rest of them. The molecular compounds are pretty straightforward. Here you have water, H2O. You all know what water looks like. You can describe its appearance, density, and melting point. Honestly, you probably already know those, maybe. If not, you can definitely look them up. It's pretty easy to find on the internet. As far as for formulas for molecular compounds, when you're given the name of simple binary molecular compounds, the prefixes tell you how many of the atoms that there are, how many atoms of each type. So tetrachloride, tetramore. So tetrachloride is 4 chlorides. Dinitrogen means 2 nitrogens. Trisulfide means 3 sulfurs. So you get the IDE endings for the second element with these as well. But the naming is actually the formula writing is actually super easy. If it doesn't have a prefix, it'll only not have a prefix on the first one. If it doesn't have a prefix on the first one, that means it only has 1. So silicon tetrachloride is going to be silicon, Si-Cl, subscript 4. Silicon tetrachloride. Dinitrogen trisulfide. Dinitrogen means 2 nitrogens in subscript 2. Trisulfide means 3 sulfurs, S subscript 3. Yeah, you're done. Pretty easy. Going to the naming of the molecular compounds, once again, also pretty easy. The only thing you have to remember is that if first element only has 1, no prefix. So first element only has 1, you don't need a prefix. You only would use the prefix mono if the second element had only 1. In this case, no prefix for the C, so this is carbon. Second element is sulfur, so there are 2 of them, so this is going to be carbon. Di is the prefix for 2, carbon disulfide. That's it. That's all you have to do. If you need a list of the prefixes, you can look at this page. It has a list of those prefixes right here. Mono, di, tri, penta, tetra, penta, etc. Carbon monoxide. The second element has 1, then you use mono. If the first element only has 1, you do not use mono. All the other prefixes are always used. So, E4, there's 4 phosphoruses, so tetra phosphorus. And 8 oxygens, oxide. Now with the oxygen, you do drop the A's. So that's one thing I should warn you about. So these prefixes are like hexa, hepta, octa, penta. Whenever you see oxygen, notice you drop that A that comes at the end would be heptoxide, hexoxide, pentoxide, tetroxide. It would not be tetraoxide. The tet A is missing. Drop the A when there's an oxide. All right, let's take a look at the next set. The molecular compound structure. So this is the end of this. It says complete the molecular compound structure table and upload it. Image of the table completed here. So for this one, you're going to want to go and look at your introductory document. This table that it's asking you to complete is this last table here, molecular compound structures. Last page. It's the last page on the introductory document. You will have to either download it or redraw it. And you will have to print it out and fill it out, or you can, like I said, print it out and scan it, print it out, fill it out and scan it, redraw it, or take a screenshot and then fill it out. But you're essentially going to have to draw the Lewis structure, indicate the steric number, the electron group arrangement. So I'll indicate what's meant by steric number, and then the number of bonded atoms, and then molecular shape, and whether it's polar or not. So let's take water for an example here. And let's see if I can draw on this. Now I'm going to go ahead and draw this out. So the electron dot structure. The first thing you want to do when drawing an electron dot structure is count the total number of valence electrons. If you look at hydrogen, hydrogen only has one valence electron. And there are two of them, so I'd say 2 times 1. Oxygen, however, has 3 valence electrons, or 6 rather, 6 valence electrons, so I'd say 1 oxygen atom times 6 valence electrons. The total number of valence electrons for water here is going to be 8. 8 valence electrons. So 8 valence electrons is how many valence electrons I have. Yeah. So now I can go ahead and start drawing what I refer to as a skeleton structure. Skeleton structure shows how the atoms are connected. Now hydrogen, usually the least electronegative atom is the central atom. An exception is hydrogen. Hydrogen can only ever form one bond. Hydrogen can never be the central atom. So in this case, oxygen has to be the central atom. And also, usually the first atom listed is the central atom. Like I said, hydrogen is an exception. So sulfur would be the central atom for this compound, nitrogen for this compound, etc. Oxygen is the central atom and is bonded to 2 hydrogens. Now, do you have to draw it like bending down like this? No, you don't. I happen to already know what the shape of this molecule is, so that's why I did it like that. If you didn't know, you might have drawn it like this, and this is perfectly fine. This is a perfectly fine skeleton structure for oxygen. What we have to remember is that every bond is actually a shared pair, or 2 electrons. So, shared pair of 2 electrons. Since I've used 4 of 8 electrons, so the remaining electrons, my remaining 4, I'm going to place in pairs on atoms that do not already have a full octet. The only one that doesn't, hydrogen only ever wants 2. It can't have 8 electrons. It can only have 2. It's an exception to the octet rule, but oxygen does want 8, so I can put more electrons than oxygen. So I'm going to put 2 lone pairs here. Now for a steric number. What is a steric number thing? You know, I never honestly heard of steric number before this lab. If you look at the procedure, rather not the procedure, but where it talks about molecular compounds and shapes and things like that, it'll talk about steric numbers. So here it says bonding and molecular structure represented as the electron dot structure. known as the Lewis structure. Each shared pair of valence electrons is represented by a line, which is what we did, to indicate electrons belong to both. A pair of electrons can be between, not necessarily. Dots will indicate unshared pairs. So, the number of valence electrons, like we build a skeleton structure, like I told you. And then add the remaining valence electrons in order to fill up the outer atoms first. So, one professor said, share with the neighbors first. But truthfully, what it comes down to is you always want to put the electrons in the most electronegative atom first. And the most electronegative atom are usually the outer atoms. This is why they say outer atoms first. More properly, it's the most electronegative atoms, the electrons first. And then you share as needed to atoms that do not have a full octet. So, this is like, for example, carbon dioxide. It says the three-dimensional shape is determined by the valence shell electron pair repulsion theory, or VSEPR, or CPR. Atoms and pairs of electrons need to spread out in space as much as possible, which occurs in predictable patterns. It says the total number of atoms and electron pairs that are bonded to an central atom is known as a steric number. So, in other words, another way to describe this would be electron domains. Okay? And so, the number of electron domains are regions of electron density. So, an electron domain can be either a lone pair or it can be a bonded pair. Now, a double bond, if I had a double bond between two atoms, okay, I had a double bond between two atoms. Let's say, for example, it was a double bond between two oxygen atoms. This double bond would still, because these electrons, the double bonded electrons, are still in the same region, this would still be one electron domain. A triple bond would also be one electron domain. So, steric number can be thought of either as the number of atoms plus the number of lone pairs bonded to the central atom, or simply the number of electron domains. In this case, the steric number is 4. 4 electron domains. As far as the electron group arrangement, this is also called the electron domain geometry. Another name for this is the electron domain geometry. I'll write that down. Electron domain geometry. Okay. So the electron domain geometry is, what is the geometry if you have 4 of them? They're going to 4 electron groups like this. So they're going to want to be as far apart from each other as possible. So this is going to be what's called tetrahedral. Tetrahedral is the shape it's going to arrange itself in if you have 4 electron domains. Now, the number of bonded atoms is only 2. So if you have a tetrahedral electron domain geometry or electron group arrangement and only 2 bonded atoms, you kind of ignore the lone pairs. So going back up to, we're taking a look at our thing here. If we look at these geometries, I have 4 electron domains. If I have only 2 bonded atoms, it's still the same shape. Those 2 atoms that are bonded are still the same shape. But the lone pairs don't count as part of the molecular geometry. So this is just going to be bent. For the molecular shape. Molecular shape is bent. Now, as far as polar or nonpolar, that's a little bit trickier to figure out. But essentially, you can easily determine whether it's polar or nonpolar by looking at the central atom. If the central atom has no lone pairs and all the atoms bonded to the outer, all the atoms bonded to the central atom are the same, this will be nonpolar. However, if there are lone pairs in the central atom, it's going to be polar. The only exception is if this is going to be polar because there's lone pairs bonded to the central atom. The only exception would be is if you have two or more lone pairs bonded to the central or connected to the central atom in such a way that they're in opposite directions. You have to remember this is tetrahedral, so they're not in opposite directions, despite what it may look like here. The shape of this molecule actually looks kind of like more like this. So you got a wedge, dash, and this is oxygen. This is hydrogen here, the hydrogen here, and then you have a group of electrons coming up like this, and a group of electrons going over like this. And so the electrons are more on one side than they are the other. And this is going to give you definitely a more negative side on, going to be a partial negative. It's going to be more negative over here, and it's going to be more positive over on the side with the hydrogen. Anytime you have one or more lone pairs on the central atom, it's usually going to be polar because of this reason. Like I said, there's very few exceptions, and there's in this particular table that's shown, there are no exceptions to that. It only has you go through the 4 domain structures, and there are no exceptions. If there's lone pairs in the central atom, it's polar. Now with 2 atom molecules like this, with 2 atom molecules like N2, the polarity of the bond is the polarity of the molecule. In other words, if the atoms are the same, it's non-polar. It's not polar because there's no electronegativity difference. If the atoms are different, then it's probably going to be polar. Well, I wish we had more time, but that is going to have to be the end of our session. I hope that this was helpful for you, and apologize if there were a few technical difficulties. Might not have seen what I was doing, but if you need any additional help, please come to the SE Science Learning Center tutoring area, and we'll be happy to go over any of that with you. For now, I'm going to go ahead and sign off and wish you all the very best. Take care. Bye-bye.